Encryption technologies. You may work for a super secret government agency, or you may be just a regular Joe or Jane citizen. Either way, you still have sensitive data that you need to protect from prying eyes. Personal secrets, government secrets, personal secrets, it doesn't matter. It all needs protection. Locking down users' home directories with restrictive permission settings, as we saw in Chapter 3, securing normal user accounts, is only part of the puzzle. We also need encryption. This encryption will provide three things for us. On confidentiality, this ensures that only people who are authorized to see the data can see it. Integrity, this ensures that the original data haven't been altered by unauthorized people. Availability, this ensures that sensitive data are always available and can't be deleted by unauthorized people. The two general types of data encryption that we'll look at in this chapter are meant to protect data at rest and data in transit. We'll begin with using file, partition, and directory encryption to protect data at rest. We'll wrap up with a look at using OpenSSL to protect data in transit. In this chapter, we'll cover the following topics: a GNU Privacy Guard, GPG, encrypting partitions with Linux Unified Key Setup, LUK, encrypting directories with eCryptFS, using Vercrypt for the cross-platform sharing of encrypted containers, OpenSSL and the public key infrastructure, commercial certificate authorities, creating key certificate requests and certificates, creating an on-premise certificate authority, adding a certificate authority to an operating system, OpenSSL and the Apache web server, setting up mutual authentication. If you're ready to crack cryptic, let's get started. GNU Privacy Guard, GPG. We'll begin with GNU Privacy Guard. This is a free open source implementation of Phil Zimmermann's Pretty Good Privacy, which he created back in 1991. You can use either of them to either encrypt or cryptographically sign files or messages. In this section, we'll focus strictly on GPG. There are some advantages of using GPG. It uses strong, hard-to-crack encryption algorithms. It uses the private-public key scheme, which eliminates the need to transfer a password to a message or file recipient in a secure manner. Instead, just send along your public key, which is useless to anyone other than the intended recipient. You can use GPG to just encrypt your own files for your own use, the same as you'd use any other encryption utility. It can be used to encrypt email messages, allowing you to have true end-to-end encryption for sensitive emails. There are a few GUI-type frontends available to make it somewhat easier to use. But, as you might know, there are also some disadvantages. Using public keys instead of passwords is great when you work directly only with people who you implicitly trust. But for anything beyond that, such as distributing a public key to the general population so that everyone can verify your signed messages, you're dependent upon a web of trust model that can be very hard to set up. For the end-to-end encryption of email, the recipients of your email must also have GCP set up on their systems and know how to use it. That might work in a corporate environment, but lots of luck getting your friends to set that up. I have never once succeeded in getting someone else to set up email encryption. If you use a standalone email client, such as Mozilla Thunderbird, you can install a plugin that will encrypt and decrypt messages automatically. But every time a new Thunderbird update is released, the plugin breaks, and it always takes a while before a new working version gets released. Even if you could get other people to set up their email clients with GPG, it's still not the perfect privacy solution. That's because the emailed metadata, the email addresses of the sender and the recipient, can't be encrypted. So hackers, advertisers, or government agencies can still see who you exchanged email messages with, and use that information to build a profile that tells them a lot about your activities, your beliefs, and what kind of person you are. If you really need complete privacy, your best bet is to go with a private messenger solution, such as the Session Messenger. That, however, is beyond the scope of this book. Even with numerous weaknesses, GPG is still one of the best ways to share encrypted files and emails. GPG comes pre-installed on most Linux distros, so you can use any of your newer virtual machines for this demos. I say newer because the procedure will differ slightly on all the distros, such as CentOS 7. Hands-on lab, creating your GPG keys. On a text mode or a Linux machine, the first thing you need to do is to install the pin entry package. Do that with sudo dnf install pin entry. Note that you won't have to do this with either a GUI mode or my Linux machine or Ubuntu server. Next, create your pair of GPG keys, GPG for generate key. Note that since you're setting this up for yourself, you don't need sudo privileges. The first thing that this command does is to create a populated GNU-PG directory in your home directory. You'll then be asked to select which kinds of keys you want. We'll just go with the default RSA and RSA. RSA keys are stronger and harder to crack than the older DSA keys. LGAML keys are good, but they may not be supported by older versions of GPG. For decent encryption, you want to go with a key of at least 3072 bits, because anything smaller is now considered vulnerable. This is according to the newest guidance from the US National Institute of Standards and Technology, or NIST. That's now the default on our newest Linux distros, so you're already good there. On all the distros, such as CentOS 7, the default is only 2048 bits, so you'll need to change it. Next, select how long you want the keys to remain valid before they automatically expire. For our purposes, we'll go with the default key does not expire. Provide your personal information. We need to generate a lot of random bytes. It is a good idea to perform some auto action, type on the keyboard, move the mouse, utilize the disks during the prime generation. This gives the random number generator a better chance to gain enough entropy. On all the Linux distros, this could take a while, even when you're doing all the recommended things to create entropy. On newer Linux distros, the random number generator works more efficiently, so you can disregard the notice about how the key generation could take a longer time. Here's what you'll see when the process has finished. Verify that the keys did get created. GPG list keys. While you're at it, take a look at the files that you created. ls-l. These files are your public and private keyrings, a revocation database, and a trusted users database. Hands-on lab. Symmetrically encrypting your own files. You may find GPG useful for encrypting your own files, even when you never plan to share them with anyone else. For this, you'll use symmetric encryption, which involves using your own private full encryption. Before you try this, you'll need to generate your keys, as I outlined in the previous section. Symmetric key encryption is, well, just that, symmetric. It's symmetric in the sense that the key that you would use to encrypt a file is the same key that you would use to decrypt a file. That's great if you're just encrypting files for your own use. But if you need to share an encrypted file with someone else, you'll need to figure out a secure way to give that person the password. I mean, it's not like you'd want to just send the password in a plain text email. In addition to your own user account, you also need a user account for Maggie. On all my Linux, create an account like this. Sudo user add Maggie, sudo password Maggie. For Ubuntu, create Maggie's account like this. Sudo add user Maggie. Let's encrypt a super secret file that we just can't allow to fall into the wrong hands. GPG-c secret squirrel stuff.txt. Note that the -c option indicates that I chose to use symmetric encryption with a passphrase for the file. The passphrase that you enter will be for the file, not for your private key. Look at your new set of files. One slight flaw with this is that GPG makes an encrypted copy of the file, but also leaves the original unencrypted file intact. ls-l. Let's get rid of that unencrypted file with shred. We'll use the -u option to delete the file and the -z option to override the deleted file with zeros. Shred -u-z secret squirrel stuff.txt. It doesn't look like anything happened because shred doesn't give you any output, but ls-l will prove that the file is gone. Now, if I were to look at an encrypted file with less secret squirrel stuff.txt.gpg, I would be able to see its contents after being asked to enter my private key passphrase. Try this for yourself. Less secret squirrel stuff.txt.gpg. As long as my private key remains loaded into my keyring, I'll be able to view my encrypted file again without having to re-enter the passphrase. Now, just to prove to you that the file really is encrypted, I'll create a shared directory and move the file there for others to access. Again, go ahead and give it a try. Sudo mkdir /shared sudo chown donny shared sudo chmod755 shared move secret squirrel stuff txt.gpg/shared. When I go into that directory to view the file with less, I can still see its contents without having to re-enter my passphrase. But now let's see what happens when Maggie tries to view the file. Use su- to switch to her account and have her try. su/Maggie cd/shared las secret squirrel stuff.txt.gpg. And when she hits the yes key to see it anyway, she gets this. Poor Maggie really wants to see my file, but all she can see is encrypted coverage. What I've just demonstrated is another advantage of GPG. After re-entering the private key passphrase once, you can view any of your encrypted files without having to manually decrypt them, and without having to re-enter your passphrase. With other symmetric file encryption tools such as bcrypt, you won't be able to view your files without manually decrypting them first. But let's now say that you no longer need to have this file encrypted, and you want to decrypt it in order to let other people see it. Exit Maggie's account by typing exit, then just use GPG with the -D option. Exit gpg-o secret squirrel stuff.txt-d secret squirrel stuff.txt.gpg. This works differently from how it worked on all the Linux distros. On our newer distros, we now have to use the -o option along with the file name of the decrypted file that we want to create. Also note that the -o option has to come before the -d option, or else you get an error message. Hands-on lab, encrypting files with public keys. In this lab, you'll learn about how to encrypt and share a file with GPG public key encryption. To begin, create a user account for Frank as you did for Maggie in the previous lab. Create a key set for both yourself and for Frank, as I've already shown you. Next, extract your own public keys into an ASCII text file. cd.gnupg gpg-export-a-o johnny public-key.txt. Log in as Frank and repeat this command for him. Normally, the participants in this would send their keys to each other either through an email attachment or by placing the keys in a shared directory. In this case, you and Frank will receive each other's public key files and place them into your respective .gnupg directories. Once that is done, import each other's keys. GPG import Frank public key.txt. Now for the good stuff. Create a super secret message for Frank's asymmetrically encrypted -e and sign it -s. Signing the message is the verification that the message really is from you rather than from an imposter. GPG-s-e secret stuff for Frank.txt. So the first thing you have to do is to enter the passphrase for your private key. Where it says to enter the user ID, enter Frank, since he is the intended recipient of your message. But look at the line after that, where it says, there's no assurance this key belongs to the named user. That's because you still haven't trusted Frank's public key. We'll get down to it a bit. The last line of the output again says to enter a user ID so that we can designate multiple recipients. But Frank is the only one you care about right now, so just hit the enter key to break out of the routine. This results in a .gpg version of your message to Frank, ls-l. The final step on your end is to send Frank his encrypted message file by whatever means available. When Frank receives his message, he'll use the -d option to view it. gpg-d secret stuff for frank.txt.gpg. Frank enters the passphrase for his private key and he sees the message. At the bottom, he sees the warning about how your public key is entrusted and that there is no indication that the signature belongs to the owner. Let's say that you and Frank know each other personally and he knows for a fact that the public key really is yours. He then adds your public key to the trusted list, cd-.gnupg gpg edit key donny jpg. The last line of this output is the command prompt for the GPG shell. Frank is concerned with trust, so he'll enter the trust command. Trust pub 2048R. Frank has known you for quite a while and he knows for a fact that you're the one who sent the key, so he chooses option 5 for ultimate trust. Once Frank logs out and logs back in, that trust will take effect. gpg-d secret stuff for frank.txt.jpg. With normal warning messages, This looks much better. At your end, you do the same thing with Frank's public key. As you can see in the screen upwards in step 8, you can assign the marginal, full, or ultimate trust level to someone else's public key. Space doesn't permit me to provide a full explanation on the trust levels, but you can read a rather colourful explanation here. PGP Web of Trust, core concepts behind trusted communication. What's so very cool about this is that even though the whole word may have your public key, it's useless to anyone who isn't a designated recipient of your message. Now let's look at how to sign a file without encrypting it. Hands-on lab signing a file without encryption. If a file isn't secret, but you still need to ensure authenticity and integrity, you can just sign it without encrypting it. Create an unencrypted message for Frank and then sign it, gpg-s not secret for frank.txt. Just as before, this creates a .gpg version of the file. Send the message back to Frank, log in as Frank, have him try to open it with less not secret for frank.txt.gpg. On all the Linux distros, you'll see a lot of gibberish because of the signature, but you'll also see the plain text message. On new Linux distros, you only see the plain text message without the gibberish. Have Frank use GPG with the verify option to verify that the signature really does belong to you. GPG verified not secret for frank.txt.gpg. This wraps it up for all discussion for encrypted individual files. Let's now take a look at encrypted block devices and directories. Encrypting partitions with Linux Unified Key Setup. LUKS. Being able to encrypt individual files can be handy, especially if you want to share sensitive files with other users, but other types of encryption are also available. Block encryption. You can use this for either whole disk encryption or to encrypt individual partitions. File level encryption. We use this to encrypt individual directories without having to encrypt the underlying partitions. Containerized encryption. Using third-party software that doesn't come up with any Linux distributions, we can create encrypted cross-platform containers that can be opened on either Linux, macOS, or Windows machines. Linux Unified Key Setup, LUKS, falls into the first category. It's built into pretty much every Linux distribution, and directions we use are the same for each. LUKS is now the default encryption mechanism for pretty much all the newest Linux distros. You might be wondering if there's any performance impact with all of this encryption business. Well, with today's fast CPUs, not really. I run Fedora with full disk encryption on a low-spec Core i5 disk laptop, and other than having to enter the disk encryption password when I first boot up, I don't even notice that encryption is taking place. Okay, let's look at encrypting on a disk while installing the operating system. This encryption during operating system installation. When you install most any Linux-based operating system, you have the option of encrypting the drive during installation. Describe the encryption option of the drive setup screen. Figure 6.1 encrypting the disk during installation. Other than that, I just let the installer create the default partitioning scheme on this Linux time machine. That means that the /file system and the swap partition will both be encrypted logical volumes. I'll cover that in a moment. Before the installation can continue, I have to create the passphrase to mount the encrypted disk. Figure 6.2, create encryption passphrase. Now, whenever I reboot the system, I need to enter this passphrase. Figure 6.3, enter the encryption passphrase. Rather than actually encrypting a normal disk partition, the installer will set up encrypted logical volumes. Once the machine is up and running, I can look at the list of logical volumes. Here, I see both the /logical volume and the swap logical volume, sudo lv display. Now let's look at the list of physical volumes. Actually, there's only one physical volume in the list, and it's listed as a LUKS physical volume, sudo pv display. In the etc directory, you'll find the crypt tab file, which contains an entry for this physical volume, sudo cat etc crypt tab. This shows that the underlying physical volume is encrypted, which means that both this root and the swap logical volumes are also encrypted. That's a good thing, because leaving the swap space unencrypted, a common mistake when setting up this encryption manually, can lead to data leakage. We'll talk about it, this crypt fault file, in just a bit. Hands-on lab, adding an encrypted partition with LUKS. There may be times where you'll need to either add another encrypted drive to an existing machine, or encrypt a portable device, such as use memory stick. This procedure works on both scenarios. Also, the procedure is the same for all of the Linux distros that we're using, so it doesn't matter which virtual machine you use. Follow these steps to add an encrypted partition. Shut down the virtual machine and add a second virtual drive. Bump the size up to 20 gigabytes, figure 6 to 5, set the size up of the new drive. After rebooting the machine, you'll now have the dev SDB drive to play with. We can see that here, ls-l. Open the drive in gdisk. Use the entire drive for the partition and leave the partition type set as default type 8300. Sudo gdisk/dev/sdb. View the details about your new dev SDB1 partition. Sudo gdisk-l dev SDB. Next, use crypt setup to convert the partition to LUKS format. In this command, the -v signifies verbose and the -i signifies that you'll have to enter your passphrase twice in order to properly verify it. Note that when it says to type yes, all in uppercase, it rarely does mean to type it in uppercase. Sudo crypt setup -v-i LUKS format. Look at the information about your new encrypted partition. Sudo crypt setup LUKS dump dev SDB1. There's a lot more to the output than I can show here, but you get the idea. Map the partition to a device name. You can name the device pretty much whatever you want. For now, just name this one Secrets. I know, it's a corny name. In real life, you won't want to make it so obvious when you're storing the secrets. Sudo crypt setup LUKS open dev SDB1 secrets. Look in the dev mapper directory. You'll see your new secrets device listed as a symbolic link to some sort of DM device. In this case, it's DM-1. cd dev mapper ls-l. Use DM setup to look at the information about your new device. Sudo DM setup info. Format the partition in the usual manner. You can use any file system that's supported by your Linux distro on a production server that will generally mean either XFS or ext4. Just fun, let's go with XFS. Sudo mkfs.xfs. Dev mapper secret. Create a mount point and mount the encrypted partition. Sudo mkdir secrets. Sudo mount dev mapper secrets. Use the mount command to verify that the partition is mounted properly. Mount pipe grep secrets. Configuring the LUKS partition to mount automatically. The only missing piece of the puzzle is to configure the system to automatically mount the LUKS partition upon boot up. To do that, configure the two different files, etc crypt tab, etc fs tab. If you encrypted the SDA drive while installing the operating system, you already have a crypt tab file that contains information about the drive. It will look something like this. The first two fields describe the name and location of the encrypted partition. The third field is for the encryption passphrase. If it's set to none, as it is here, then the passphrase will have to be manually entered upon boot up. In the fs-tab file, we have the entry that actually mounts the partition. Well, there are actually two entries in this case because we have two logical volumes, root and swap, on top of the encrypted physical volume. The UUID line is the /boot partition, which is the only part of the drive that isn't encrypted. Now, let's add our new encrypted partition so that it will mount automatically as well. Hands-on lab, configuring the LUKS partition to mount automatically. In this lab, you'll set up the encrypted partition that you created in the previous lab to automatically mount when you reboot the machine. This is where it would be extremely helpful to remotely lock in your virtual machine from your desktop host machine by using a GUI type terminal, be it terminal from a Linux or macOS machine or Segwin from a Windows machine. You'll have the ability to perform copy and paste operations which you won't have if you work directly from the virtual machine terminal. Trust me, you don't want to be typing in those long UUIDs. The first step is to obtain the UUID of the encrypted partition. Sudo crypt setup LUKS IDs. Copy that UUID and paste it into the etc crypt tab file. If a crypt tab file isn't already there, just create a new one. Also, note that you'll paste the UUID in twice. The first time it will be prepended with the LUKS, and the second time you'll append it with UUID. Edit the etc fs tab file, adding the last line in the file for your new encrypted partition. Note that you again have to use LUKS followed by the UUID number. When editing the tab file for adding normal unencrypted petitions, I always like to do sudo mount-a to check the fs tab file for typos. That won't work with Lux petitions though, because mount won't recognize the petition until the system reads in the crypt tab file, and that won't happen until I reboot the machine. So just be extra careful with editing fs tab when adding Lux petitions. Now for the moment of truth. Reboot the machine to see if everything works. Use the mount command to verify that your endeavors have been successful. Mount, pipe, grab secrets. Enter flag. Tip. Although it is possible to include passwords or keys in the etc crypto file, my preference is not to do so. If you must do so, be sure that the passwords or keys are stored on an encrypted /petition, for which you'll always have to enter a password upon boot up. You can read more about that here. Store the passphrase of encrypted disk in etc crypt tab encrypted. Now that we've seen Lux, let's move on to encryptfs. Encrypting directories with encryptfs. Encrypting entire petitions is cool, but you might at times just need to use file level encryption to encrypt an individual directory. For that, we can use encryptfs. We'll need to use our Ubuntu machines for this because Red Hat and its offering no longer include encryptfs. It was in Red Hat 6 and CentOS 6, but no longer even available for installation in any newer versions. Tip. It's possible to use encrypt on a Lux encrypted disk, but it's not at all necessary, and I really don't recommend it. Hands-on lab, encrypting a home directory for a new user account. In Chapter 3, Securing Normal User Accounts, I showed you how Ubuntu allows you to encrypt a user's home directory as you create his or her user account. To review, let's see the command for creating Gordy's account. If it hasn't already been done, install the encryptfs utils package, sudo apt install encryptfs utils. On an Ubuntu VM, create Gordy's account with an encrypted directory, sudo @user encrypt home Goldie. Have a Goldie login. Have her unwrap her mount passphrase. Write it down and store it in a secure place. She'll need it if he ever needs to recover a corrupted directory. Encryptfs unwrap passphrase. Encryptfs wrap passphrase. When you use @user encrypt home directories for new users will automatically be set to a restricted permissions value that will keep everyone out except for the owner of the directory. This happens even on Ubuntu 20.04 when you leave the @user.conf file set with its default settings, creating a private directory within an existing home directory. Let's say that you have users on your Ubuntu servers who, for whatever strange reason, don't want to encrypt their entire home directories and want to keep the 755 permission settings on their home directory so that other people can access the files. But they also want a private directory that nobody but them can access. Instead of encrypting an entire home directory, any user can create an encrypted private directory within his or her own home directory. Let's check it out. If it hasn't already been done, install the encryptfs utils package, sudo apt install encryptfs utils. To create this private directory, use the interactive encryptfs setup private utility. If you have admin privileges, you can do this for all the users. Users without admin privileges can do it for themselves. For our demo, let's say that Charlie, my big CMS great tabby guy, needs his own encrypted private space. Who knew that cats had secrets, right? Create Charlie's account in a normal manner without the encrypted home directory option. Then log in as Charlie and have him create his own private directory. Encryptfs setup private. For the login passphrase, Charlie enters his normal password or passphrase for logging into his user account. He could have let the system generate his own mount passphrase, but he decided to enter his own. Since he did enter his own mount passphrase, he didn't need to do the encryptfs unwrap passphrase command to find out what the passphrase is. But just to show how that command works, let's say that Charlie entered turkeylips as his mount passphrase, encryptfs unwrap passphrase. Yes, it's a horribly weak passphrase, but for our demo purposes it works. Have Charlie log out and then log back in. After this, he can start using his new private directory. Also, you can see that he has 3 new hidden directories within his own directory. All 3 of these new directories are only accessible by Charlie, even if he set his top-level home directory so that it's open to everybody. ls-la. Run the grep encryptfs star command in the etc pam.d directory. You'll see that PAM is configured to automatically mount users' encrypted directories whenever they log into the system. End of the lab. Alrighty then. We now know how to encrypt users on directories. Now, let's find out how to encrypt others' directories. Hands-on lab, encrypting other directories with eCryptFS. Encrypting other directories is a simple matter of mounting them with the eCryptFS file system. Create a secrets2 directory in the top level of the file system. Sudo mkdir secrets2. Use mount with the -t encryptfs option to encrypt the directory. Note that you list the directory name twice because then it will be used as its own mount point. From the menu, choose one to enter your desired passphrase and choose the encryption algorithm and the key length. Sudo mount -t encryptfs secrets2 secrets2. Go with the default of AES and 16 bytes for the key. Go with the default of no for plaintext pass-through and with yes for file name encryption. Go with the default file name encryption key and verify the mounting options. This warning only comes up when you mount the directory for the first time. For the final two questions, type yes in order to prevent that warning from coming up again. Just for fun, create a file with your new encrypted secrets2 directory and then unmount the directory. Then try to do a directory listing. cd secrets2 sudo vim secretstuff.txt cd sudo unmount secrets2 ls-l secrets2. By choosing to encrypt file names, nobody can even tell what files you have when the directory is unmounted. When you are ready to access your encrypted files again, just remount the directory the same as you did before. Encrypting is swap partition with eCryptFS. If you're just encrypting individual directories with eCryptFS instead of using LUKS for this encryption, you'll need to encrypt your swap partition in order to prevent accidental data leakage. Fixing that problem requires just one simple command. Sudo eCryptFS-setup the swap. Don't mind the warning about the missing dev mapper crypt swap1 file. It will get created the next time you reboot the machine. Using VeriCrypt for cross-platform sharing of encrypted containers. Once upon a time, there was TrueCrypt, a cross-platform program that allowed the sharing of encrypted containers across different operating systems. But the project was always shrouded in mystery because its developers would never reveal their identities. And then, right out of the blue, the developers released a cryptic message about how TrueCrypt was no longer secure and shut down the project. VeriCrypt is the successor of TrueCrypt, and it allows the sharing of encrypted containers across Linux, Windows, macOS, and FreeBSD machines. Although LUKS and eCryptFS are good, VeriCrypt offers more flexibility in certain ways. As mentioned, VeriCrypt offers cross-platform sharing, whereas LUKS and eCryptFS don't. VeriCrypt allows you to encrypt either whole partitions or whole storage devices, or to create virtual encrypted disks. Not only can you create encrypted volumes with VeriCrypt, you can also hide them, giving you plausible deniability. VeriCrypt comes in both command line and GUI variants, so it's appropriate for either server use or for the casual desktop user. Like LUKS and eCryptFS, VeriCrypt is free open source software, which means that it's free to use and that the source code can be audited for either bugs or backdoors. Hands-on lab getting and installing VeriCrypt. Follow these steps to download VeriCrypt. Download VeriCrypt here. The Linux version of VeriCrypt comes two ways. First is a tar.bz2 file, which contains a set of universal style scripts that should work on any Linux distribution. Once you extract the tar.bz archive file, you'll see 3 scripts for GUI installation and 2 for console mode installation. There are scripts for both 32-bit and 64-bit versions of Linux. tar xjvf VeriCrypt. The executable permission is already set, so all you have to do to install is this. /vercrypt GUI x64. You'll need sudo privileges, but the installer will prompt you for your sudo password. After reading and agreeing to a rather lengthy license agreement, the installation only takes up a few seconds. Optional step. Recently, the VeriCrypt developers added a second way to install VeriCrypt on Linux. On the download page, you'll now see that there are .dev and .rpm package files for various versions of Debian, Ubuntu, OpenSUSE, and Red Hat CentOS Fedora. For Debian Ubuntu systems, install the package by doing sudo the package -i vercrypt package version.dev. For RHEL, CentOS, Fedora, and OpenSUSE, do sudo rpm -uvh vercrypt package version.rpm. Note though that there's still nothing here for the newer Red Hat 9 type distros, but I found that the CentOS 8 package does work on Linux 9. End of the lab. More recently, the Vercrypt developers have also begun supplying .deb and .rpm installer packages for specific Linux distros. For Debian Ubuntu type systems, use sudo dpackage.i to install the .deb file. On RHEL, CentOS, or Linux SUSE systems, use sudo rpm-uvh to install the rpm file. Note that you might receive an error message telling you to install all the packages as dependencies. Also note that there is no .rpm package for the RHEL or Linux distros. Not to worry though, because I've just verified the CentOS package works just fine on Linux 9. Hands-on lab, creating and mounting a Vercrypt volume in console mode. I haven't been able to find any documentation for the console mode variant of Vercrypt, but you can see a list of the available commands just by typing Vercrypt. For this demo, you'll create a 2 GB encrypted directory, but you can just as easily create an encrypted directory elsewhere, such as on a USB memory stick. To create a new encrypted volume, type the following, vercrypt-c. This will take you into an easy-to-use interactive utility. For the most part, you'll be fine just accepting the default options for vercrypt-c. For the file system, the default option of FAT gives you the best cross-platform compatibility between Linux, macOS, and Windows. Select your password and a PIM, short for Personal Iterations Multiplier. For my PIM, I entered 8891. Higher PIM values give better security, but it will also cause the volume to take longer to mount. Then, type at least 320 random characters in order to generate the encryption key. This is where it would be handy to have my cats walking across my keyboard. After you hit the enter key, be patient because the final generation of your encrypted volume will take a few moments. Here you see that my 2 GB good stuff container has been successfully created. ls-l good stuff. Mount this container in order to use it. Begin by creating a mount point directory, macdir good stuff dir. Use the Vercrypt utility to mount your container on this mount point. Vercrypt good stuff dir. To see what Vercrypt volumes you have mounted, use vercrypt-l. End of the lab. That's all there is to it. Using Vercrypt in GUI mode. Desktop users of any of the supported operating systems can install the GUI variant of Vercrypt. Be aware though that you can't install both the console mode variant and the GUI variant on the same machine because one will override the other. Here's what that looks like. Figure 6.6 Vercrypt control panel. Since the main focus of this book is server security, I won't go into the details of the GUI version here, but it's fairly self-explanatory and you can view the full Vercrypt documentation on their website. You can get Vercrypt from here. OpenSSH and the public key infrastructure. With OpenSSH, we can encrypt information on the fly as it goes across the network. There's no need to manually encrypt our data before we send them across the network because OpenSSL encryption happens automatically. This is important because online commerce and banking couldn't exist without it. The Secure Sockets Layer SSL is the original in-transit encryption protocol. Ironically, even though we're using the OpenSSL suite of programs and libraries, we no longer want to use SSL. Instead, we now want to use the Transport Layer Security (TLS) protocol. SSL is full of legacy code and a lot of vulnerabilities that go along with that legacy code. TLS is newer and much more secure, but even when working with TLS, we can still use the OpenSSL suite. One reason that the older SSL protocol is so bad is because of past government regulations, especially here in the US, that prohibited the use of strong encryption. For the first few years of the public internet, US website operators couldn't legally implement encryption keys that were longer than a measly 40 bits. Even back then, a 40-bit key didn't provide a whole lot of security. But the US government considered strong encryption as a type of munition and tried to control it so that the government of other countries couldn't use it. Meanwhile, an Australian outfit named Fortify started producing a strong encryption plugin that people could install on the Netscape web browsers. This plugin allowed the use of 128-bit encryption, and my geek buddies and I all eagerly installed it on our own machines. Looking back, I'm not sure that it did a lot of good, because website operators in the US were still prohibited from using strong encryption keys on their web servers. Amazingly, the Fortify outfit still has their website up. You can still download the Fortify plugin even though it's not completely useless. Here's a screenshot of the Fortify website. Figure 6.7, the Fortify.net website. An encrypted SSL TLS session uses both symmetric and asymmetric mechanisms. For acceptable performance, it uses symmetric encryption to encrypt the data in transit, but symmetric encryption requires a private key to be exchanged between the two communication partners. To do that, SSL TLS fails to negotiate an asymmetric encryption using the same public key exchange mechanism that we look at in the GPG section. Once the asymmetric session is set up, the two communication partners can safely exchange the private key that they'll use for the symmetric session. Commercial certificate authorities. To make this magic work, you need to install a security certificate onto your web server. The certificate serves two purposes. It contains a public key that's needed to set up an asymmetric key exchange session. Optionally, it can verify the identity of or authenticate your website. So, for example, users can theoretically be sure that they're connected to the real bank instead of the Joe Hacker's banks of crooks and criminals that's disguised as their bank. When you shop for a certificate, you find quite a few vendors which are all referred to as certificate authorities or CAs. Most CAs, including vendors such as Tevault, Symantec, GoDaddy, and Let's Encrypt, among others, offer several different grades of certificates. To help explain the differences between the grades of certificates, here's a screenshot from the GoDaddy site. Figure 6.8, certificate pricing. At the left-hand side of the list, at the cheapest price, is the standard domain verification, DV, offering. Vendors advertise this type of certificate for use where all you really care about is encryption. Identity verification is limited to domain verification, which means that records for your site have been found on a publicly accessible DNS server. At the right, we see the Premium Extended Verification EV offering. This is the top of the line, the highest grade certificate that certificate vendors offer. With this extended verification grade certificate, you have to jump through some hoops to prove that you are who you really are and that your website and your business are both legit. It used to be that both Firefox and Chrome would show a green high assurance bar on the URL of any site with an EV certificate, but they no longer do for reasons I'll explain in a moment. So just how good is this Premium SSL EV certificate with rigorous identity testing? Well, not quite as good as I thought. 2 days after I wrote this explanation about the different types of certificates for the previous edition of this book, I received the latest edition of the Bulletproof TLS newsletter from Faisley Duck Publishing. The big news was that Google and Mozilla decided to remove the green high assurance bar from future editions of Chrome and Firefox. The reasons were as follows. The green high assurance bar was meant to help users avoid phishing attacks, but for that to be useful, users had to notice that the high assurance bar was even there. Studies have shown that most people didn't even notice it. Ian Carroll, a security researcher, questions the value of extended validation certificates. As an experiment, he was able to register a bogus certificate for Stripe.inc, which is a legitimate company. The certificate vendor finally did notice their mistake and revoked the certificate, but something that shouldn't have happened in the first place. On top of everything else, it was also possible to register extended validation certificates with incorrect information. This indicated that the verification process isn't quite as thorough as the certificate vendors would have us believe. But in spite of these occasional problems, I still believe that extended validation certificates are useful. When I access my bank account, I like to believe that extra identity verification is never a bad thing. Something else that's rather curious is that certificate vendors still market their certificates as SSL certificates. Don't be fooled though, as long as the website owners configure the service correctly, they'll be using the more secure TLS protocol rather than SSL. Let's Encrypt is a fairly new organization that has the goal of ensuring that all websites everywhere are set up with encryption. It's a worthy goal, but it has also introduced a new problem. Here's what the Let's Encrypt website looks like. Figure 609 is the Encrypt homepage. To obtain a certificate from one of the traditional vendors, you have to use the OpenSSL utility to create your keys in a certificate request. Then you'll submit the certificate request, proof of identity if applicable, and your payment to the certificate authority. Depending upon which grade of certificate you purchase, you have to wait anywhere from 1 to several days before you get the certificate. Unlike the traditional certificate vendors, Let's Encrypt is totally free of charge and you don't have to jump through hoops to get the certificate. Instead, you configure your web server to automatically obtain a new Let's Encrypt certificate each time you set up a new website. If Let's Encrypt sees that your new site has a valid record on a publicly accessible DNS server, it will automatically create and install a certificate in your web server. Other than having to configure your web server to use Let's Encrypt, it's no fuss, no muss. The problem with Let's Encrypt is that it's even easier to abuse than extended validation certificates. Shortly after Let's Encrypt began operation, criminals began setting up domains that appear to be subdomains of legitimate business sites. So people see that the website is encrypted and that the domain name seems to be legit, and they merely enter their credentials without giving things a second thought. Let's Encrypt is handy and useful for legitimate purposes, but beware of its downside too. Tip: before you choose a certificate vendor, do some research. Sometimes even the big name vendors have problems. A few years ago, Google removed Symantec from Chrome's list of trusted certificate authorities because Symantec had allegedly violated industry best practices several times. This is rather ironic to consider that Symantec has had a long history of being a trusted vendor of security products. Now that we've covered the basics of SSL TLS encryption, let's see how to implement it with the OpenSSL suite. Creating keys, certificate signing requests, and certificates. The good news is that regardless of which newer Linux distributions we're on, this procedure is the same. I say newer because the newest versions of Ubuntu and RHEL or Linux use OpenSSL version 3. Some of the version 3 commands are different from what you'll see on the older versions. The not so good news is that OpenSSL can be a bit tricky to learn because it has loads of subcommands, each with its own set of options and arguments. Bear with me and I'll break it down the best I can. Creating a self-signed certificate with an RSA key. A self-signed certificate is useful when all you need is encryption or for testing purposes. Here's no identity verification involved with self-signed certificates, so you'll never want to use them on servers that your users need to trust. Let's say that I need to test my new website set up for putting it into production and I don't want to do my testing with a full real key and certificate. I'll create the key and the self-signed certificate with one single command. OpenSSL req-new key RSA column 2048-nodes -key out .domain.key x509/days 365-out domain.crt. Here's the breakdown. OpenSSL. I'm using OpenSSL with just my normal user privileges. For now, I'm doing everything in my own home directory, so there's no need for root or sudo privileges. Rec. This is a subcommand for managing certificate filing requests, CSRs. When creating self-signed certificates, OpenSSL will create a temporary CSR. New key RSA 2048. I'm creating an RSA key pair that's 2048 bits in length. I actually like to use something a bit longer, but that might impact server performance when setting up the TLS handshake. Again, this is preceded by only a single dash nodes. This means that I'm not encrypting the private key that I'm about to create. If I were to encrypt the private key, I would have to enter the private key passphrase every time I restart the web server. Key domain key x509. I'm creating the private key with the name domain key 509. The x509 part indicates that this will be used for a self-signed certificate. Base 365, the certificate will expire 1 year. Out domain CRT. Finally, I'm creating a domain CRT certificate. When you run this command, you'll be prompted to enter information about your business and your server. We'll look at that in just a moment. After creating this key and certificate, I'll need to move them to the proper locations I configure my web server to find, and we'll also touch on that in that bit. Encrypting the private key is an optional step, which I didn't do. If I were to encrypt the private key, I would have to enter the passphrase every time I restart the web server. That could be problematic if there are any web server admins who don't have the passphrase. And even though this sounds counterintuitive, encrypting the private key that's on the web server doesn't really help that much with security. Any malicious person who can get physical access to the web server can use memory forensics tools to get the private key from some symmetric system memory, even if the key is encrypted. But if you plan to make a backup of the key to store somewhere else, definitely encrypt that copy. So now let's make an encrypted backup copy of my private key that I can safely store somewhere other than on the web server. There are two things to look at here. RSA AES256 means that I'm using the AES256 encryption algorithm to encrypt an RSA key. To ensure that I make a copy instead of overwriting the original unencrypted key, I specify domain encrypted key x509 as the name of the copy, creating a self-signed certificate with an elliptic curve key. RSA keys were okay in their day, but they do have their disadvantages. I'll cover this more in just a bit. Elliptic curve EC keys are superior in pretty much every way. So let's now create a self-signed certificate with an EC key instead of with an RSA key, like so. The only part of this that's different is the EC OpenSSL EC param named SecP38-4R1 part. It looks strange, but it's really quite logical. When creating an EC key, you have to specify a parameter with the EC param command. You'll normally see this as two separate OpenSSL commands, but it's handier to combine the two commands together as one command within another command. The inner OpenSSL command is feeding its output back to the outer OpenSSL command via the input redirection symbol, less than sign. The -name pod means that we're creating a 3 188-bit EC key with the SECP384 named curved algorithm, creating an RSA key and a certificate signing request. Normally, we won't use a self-signed certificate for anything that's meant for the general public to interface with. Instead, we want to obtain a certificate from our commercial CA because we want users to know that they're connected to a server for which the identity of its owner has been verified. To obtain a certificate from a trusted CA, you'll first need to create a key and a certificate signing request, CSR. Let's do that now. OpenSSL rec out csr.csr new key RSI248 nodes key out server private key.key. Here with the breakdown. OpenSSL, I'm using OpenSSL with just my normal user privileges. For now, I'm doing everything in my own home directory, so there's no need to root or sudo privileges. Rec, this is the subcommand for managing CSRs. Out csr.csr. The out means that I'm creating something. In this case, I'm creating the CSR with the name csr.csr. All CSRs will have the CSR file name extension. New, this is a new request. And yes, this is preceded by a single dash, unlike the out in the previous line is preceded by 2 dashes. New key RSA248. We're creating an RSA key pair that's 2048 bits in length. I'd actually like to use something a bit longer, but that will impact server performance when setting up the TLS handshake. Again, this is preceded by only a single dash. Nodes. This means that I'm not encrypting the private key that I'm about to create. If I were to encrypt the private key, I would have to enter the private key passphrase every time I restart the web server. Key out server private key.key. Finally, I'm creating the private key with the same server private key.key. Since this key isn't for self-signed certificate, I didn't put the X509 at the end of the key's file name. Let's now look at a snippet from the original output. OpenSSL request out csr.csr new key RSI228 nodes key out server private key.key. So I've entered my information about my company location, name, and website name. Note at the bottom where it asks me for a challenge password. This password doesn't encrypt either the key or the certificate, rather it's just a shared secret between the certificate authority and me that's embedded into the certificate. I'll need to keep it in a safe place in case I ever need to reinstall the certificate, and for goodness sake, when you do this for real, pick a better password than turkey lips. As before, I didn't encrypt the private key, but if you need to make a backup copy, just follow the procedure that you saw in the previous section. To obtain a certificate from a commercial CA, go to the website and follow the directions. When you receive your certificate, install it in the proper place on your web server and configure the web server to find it, creating an EC key and a CSR. Up until a few years ago, you would have wanted to use RSA keys in your web servers. They don't have the security weaknesses that certain other key types have, and they're widely supported by pretty much every web browser. But RSA keys do have 2 weaknesses. Even at the standard 2048-bit length, they require more computational power than other key types. Increasing the key length for better security could degrade server performance. RSA doesn't offer a perfect forward secrecy PFS. In other words, if someone were to capture a session key that's produced by the RSA algorithm, they would be able to decrypt the material from the past. If the same person were to capture a session key that was produced by a PFS algorithm, they would only be able to decrypt the current communication stream. Using the new fangled EC algorithms instead of the creaky old RSA solves both of these problems, but if you pick up a book from even a couple of years ago, you'll see that it recommends using RSA keys for backward compatibility with all the web browsers, partly because certain operating systems, along with their associated proprietary web browsers, lingered on for far longer than they should have. I'm looking at you, Windows XP. Now though, as I sit here writing this in October 2022, I think it's safe to start ignoring the needs of anyone who refuses to move on these antiquated platforms. I mean, Windows XP and Windows 7 both reached the end of life several years ago. So let's get with the times, people. Unlike what we just saw with the RSI keys, we can't create the EC private key and the CSR all with one single command. With EC, we need to do this in 2 separate steps. First, I create a private key. OpenSSL gen pkey algorithm EC out eckey.pem pkey opt EC pargem curve p384 pkey.opt EC parm enc named curve. Here's the breakdown. GENP key algorithm EC. The genp key command is a fairly recent addition to OpenSSL and is now the recommended way to create private keys. Here I'm telling it to create a key with the EC algorithm. Out eckey.pem. I'm creating the eckey.pem key, which is in the privacy enhanced mail format. The RSI keys I created in the previous section were also PEM keys, but I used the key file name extension on them. You can either the key or the PEM file extension and they'll both work. But if you use the PEM extension, everyone who looks at them can tell at a glance that they are PEM keys. P-key opt EC perm gen curve P384. This tells OpenSSL to create an EC key that's 384 bits in length. A beautiful thing about EC is that its shorter length keys provide the same encryption string as the longer RSA keys. In this case, we have a 384-bit key that's actually stronger than 2048-bit RSA key, and it requires less computational power. I call that a total win. P-key opt ECPerm ENC named curve. This is the encoding method I'm using for the EC parameters. It has to be set to either named curve or explicit. Now I'll create a CSR and sign it with my new private key like so. OpenSSL rec new key eckey.pem out eckey.csr. The output that it didn't include is the same as what you saw in the RSA key encryption key section. And the final steps are the same as before. Choose a CA and let them tell you how to submit the CSR. When they issue the certificate, install it on your web server. Creating an on-premise CA. Buying a certificate from a commercial CA is good when you're dealing with the general public on a website that they need to trust. Well, for an organization's own internal use, it's not always necessary or feasible to buy commercial certificates. Let's say that your organization has a group of developers who need their own client certificates to access the development server. Buying a commercial certificate for each developer would be costly, and it would require the development server to have a publicly accessible domain name so that the commercial CA can do domain verification. Even going with the free of charge less encrypt certificates isn't a good option because that would also require the development server to have a publicly accessible domain name. Option 2 is to go with self-signed certificates. But that won't work because client authentication doesn't work with self-signed certificates. That leaves option 3, setting up a private on-premise CA. If you search around on the web, you'll find lots of guides for setting up your own private CA, but almost all of them are woefully outdated, and most of them are set for setting up a CA with OpenSSL. There's nothing wrong with using OpenSSL for CA, except that setting it up is a rather convoluted multi-stage process. Then when you finally do have to set it up, you have to use complex commands from the command line in order to do anything. What we want is something a bit more user-friendly for both you and your users. Hands-on lab setting up a DocTag CA. DocTag PKI is much simpler to set up, and it has a nice web interface that OpenSSL doesn't have. It's available in the normal repositories of Debian, Ubuntu, and RHEL or Linux, but under different package names. In the Debian Ubuntu repositories, the package name is doctag-pki. In the RHEL or Linux repositories, the name is pki-ca. For some reason that I don't understand, you'll never see Red Hat Folk use the doctag name. Before we install the doctag packages, we need to do a couple of simple chores. Set a fully qualified domain name, FQDN, on the server. Either create a record in a local DNS server for the doctag server or create an entry for it in its own etc host file. You can do this on either your Linux 9 or on your Ubuntu 22.04 VM, and I'll give directions for both. To access the doctag dashboard, we'll use the second Linux VM with a desktop environment installed. With all this out of the way, let's get started. On your server virtual machine, set a fully qualified domain name, substituting your own for the one that I'm using. Sudo hostname ctl set hostname .eca.local. Edit the etc host file to add a line like the following: 192.168.053.eca.local. Use your virtual machine's own IP address and fully qualified domain name. Next, increase the number of file descriptors that your system can have open at one time. Otherwise, you get a warning message when you run the directory server installer. Do that by editing the etc security limits.com file. At the end of the file, add these two lines: root hard no file 4096, root soft no file 4096. Reboot the machine so that the new hostname and file descriptor limits can take effect. DocTag stored its certificates and user information in an LDAP database. In this step, we'll install the LDAP server package along with the doctag passive package. For Linux 9, do this: sudo dnf install 389 dsbase pka.ca. For Ubuntu 22.04, do this: sudo apt install 389 dsbase doctag pka. Next, create an LDAP directory server ds instance by first creating an instance.inf file in the root user's home directory. Sudo vim root instance.inf. Make its contents look something like this, using your own suffix and root password. Yes, I know that's a bad practice to put passwords into plain text configuration files. That's okay though, we'll take care of that in just a bit. We can now use this instance.inf file along with the dscreate utility to create the directory server instance. Sudo dscreate from file root instance.inf. Finally, it's time to create the CA. Sudo pki spawn. Accept all the defaults until you get to the very end. When it asks begin installation, type yes. When you get to the directory server part, enter the password that you used to create the DS instance in the previous tab. Note that you will be offered the choice to access the LDAP DS instance via a secure port, but since we're setting up LDAP and DocTAG on the same machine, it isn't necessary. Ensure that the DocTAG service will automatically start by enabling the PKI tomcat-d target. Do that with sudo systemctl enable keep PKI tomcat-d.car target sudo shutdown-r now. After everything's set up, you no longer need the instance.inf file that holds your password in plain text. Get rid of it by doing sudo shred-u-z root instance.inf. You'll access the DocTAG web interface via port 8443 TCP. On the Oma Linux machine, open that port like this: sudo firewall cmd permanent at port 8443 TCP sudo firewall cmd reload. On the Ubuntu machine, assuming that you're using the uncomplicated firewall, open the port like this: sudo ufw allow 8443 TCP. On another Linux virtual machine that has this desktop interface, edit the etc host file to add the same name that you added to the server host file in step 2. Then open a firewall's web browser on that machine and navigate to the DocTAG dashboard. In keeping with the example in this scenario, the URL will look like this: donny-ca.local port 8443. You'll receive a warning about the certificate being invalid because it's a self-signed. That's normal because every CA has to start with a self-signed certificate, and you haven't yet imported the certificate into your trusted store. Temporarily add the exception and continue. In other words, clear the checkmark from the add permanently box. You'll see why in the next lab. Click through the links until you reach the screen. Figure 6.10 local certificate server. Click the SSL end user services link. This is where end users can request various types of certificates. Click the back button to return to the previous screen. This time click on the agent services link. You won't be able to go there because it requires you to install a certificate into your web browser for authentication. The certificate that you need to install is in the root doctag PKI tomcat directory of your doctag VM. Copy this file to the VM on which you're using Firefox to access the doctag dashboard. Do the following: sudo su-cd root doctag PKI. Of course, substitute your own username and IP address. Note that the file will automatically land in your own home directory and that its ownership will change from root to your own username. On the VM with Firefox, import the certificates into Firefox. From the Firefox menu, choose Settings and then Privacy and Security. At the very bottom of the screen, click on View Certificate. Click the Your Certificates tab at the top and the Import button at the bottom. Navigate to your home directory and choose the certificate that you just sent over from the DocTAG server VM. Once the import operation is complete, you should see the PKI administrator certificate in the list of imported certificates. Figure 6.11's Local Certificate Manager. Now try to access the agent services page. You'll be allowed access once you confirm that you want to use the certificate that you just imported. End of the lab. When a user needs to request a certificate for their own use, they'll use OpenSSL to create a key and then the CSR, as I've already shown you earlier in this chapter. Then they'll go to the SSL and user services page and paste the contents of their CSR into the box for the certificate that they're requesting. And the administrator will then go to the agent services page to approve the request and issue the certificate. To help familiarize yourself with DocTAG, I encourage you to click around on the web interface, exploring all the options. Adding a CA to an operating system. Most of the major web browsers, such as Firefox, Chrome, and Chromium, come with their own predefined databases of trusted CAs and their associated certificates. When you create a private CA, you'll need to import a CA certificate into your browser's trust store. Otherwise, your users will keep receiving messages about how the site is dead. They're viewing or using untrusted certificates. Indeed, that is the case with our DocTAG server. Any user who accesses it to request a certificate will receive a warning about how this CA is using a non-trusted certificate. We'll fix that by exporting the CA certificate from the DocTAG server and importing it into all of your users' browsers. Let's dig in, shall we? Hands-on lab, exporting and importing the doctac CA certificate. The doctac web portal doesn't have an option for this, so we'll have to use the command line. In your home directory of the doctac server, create a passport.txt file. On the first line of the file, set the password for the server certificate. It's the password that you set when you ran the pki spawn command. Extract the server key and certificate like so. Sudo pki server csh chain export pkcs12 file pki server p.12 pkcs12 password file password.txt. Run an ls-l command to verify that the pki server.p12 file was created. The problem with the P12 file is that it contains both server's private key and a certificate, but to add a certificate to the CA section of the browser's trusted store, you have to have just a certificate without the key. Extract the certificate like so. Open SSL pkcs12 info in pki server p12 out. pk server cert no keys. Transfer this new PK server CRT file to a machine with a graphical desktop. In Firefox, open Settings, Privacy and Security. Let's click the View Certificates button at the bottom. Click the Authorities tab and import the new certificates. Select Trust the CA to identify websites and Trust the CA to identify email users. Figure 6 of 12, Local Certificate Manager. Close Firefox and open it again to ensure the certificate takes effect. Navigate to the doctac portal. This time you shouldn't receive any warning messages about using an untrusted certificate. End of the lab, importing the CA into Windows. With either Firefox or Chrome, you'll import the CA certificate directly into the browser's trusted store, regardless of which operating system you're running. But if you're stuck running one of Microsoft's own proprietary browsers on that off-brand operating system that's known as Windows, then you'll need to import a certificate into the Windows trusted store instead of into the browser. Fortunately, that's incredibly easy to do. After you copy the certificate to the Windows machine, just open up Windows File Explorer and double-click the certificate file. Then click the Install Certificate button in the pop-up dialog box. If your organization is running an Active Directory domain, just ask one of the AD administrators to import it into the Active Directory for you. Open SSL and the Apache web server. The default installation of any web server isn't all that secure, so you'll need to harden it up a bit. One way to do that is by disabling the weaker SSL TLS encryption algorithms. The general principles apply to all web servers, but for our examples, we'll just look at Apache. The topic of web server hardening is quite extensive. For the present, I'll confine the discussion to hardening the SSL TLS configuration. You can use either Ubuntu 22.04 or Linux 9 for this section, but the package names and configuration files are different between the two distros. The configurations are also differ between CentOS 7 or Linux 9, so we'll look at them as well. But before I can explain the configuration options, I need to say a word or two about the history of the SSL TLS protocol. In the 1990s, engineers at Netscape invented the SSL protocol. Version 1 never saw the light of day, so the first release version was SSL version 2, SSL v2. SSL v2 had its share of weaknesses, many of which were addressed in SSL v3. At the insistence of Microsoft, the next version was renamed Transport Layer Security TLS version 1. I have no idea why Microsoft objected to the SSL name. The current version is TLS 1.3, which is finally now supported by most Linux distros. By default, Apache supports one of the older protocols. Our goal is to disable those older protocols. Only a couple of years ago, that would have meant disabling SSL v2, SSL v3, and leaving TLS v1 through TLS v2 due to questionable browser support for anything newer. Now though, I think it's safe to disable support for anything older than TLS v3, 1.3. When I wrote the second version of this book back in 2019, Apple Safari was the only major browser that didn't support TLS v1.3. Fortunately, even Apple is now on board with the newest TLS. Hardening Apache SSL TLS on Ubuntu. For this demo, we'll use two Ubuntu 22.04 virtual machines. We'll install Apache on the first one and SSL scan on the second one. This SSL scan package isn't available in the Linux repository. To install Apache on your Ubuntu machine, just do the following: sudo apt install Apache 2. This also installs the mod SSL package, which contains libraries and commercial stuff with SSL TLS implementation. And of course, if you have a firewall enabled, be sure that port 443 TCP is open. The Apache server is already enabled and running, so you don't have to mess with that. But you do need to enable the default SSL site and the SSL module with these three commands: sudo a2 and site, default SSL conf with sudo a2 and mod, sudo systemctl restart Apache 2. Before we look at the SSL TLS configuration, let's set up a scanner machine to externally test our configuration on the second Ubuntu VM and install the SSL scan package. Sudo apt install SSL scan. On the scanner machine, scan the Ubuntu machine on which you installed Apache, substituting the IP address of your machine. Sudo SSL scan 192.168.0.3. Note the algorithms and the protocol versions that are supported. You should see that SSL v2, SSL v3, TLS 1.0 and TLS 1.1 are all disabled. TLS 1.2 and TLS 1.3 are the only ones that are enabled. On the Ubuntu VM with Apache, edit the etc apache mods enable ssl.conf file. Look for the line that says this, SSL protocol or SSL v3. Change it to this, SSL protocol or SSL v3 TLS v1.2. Restart the Apache daemon to make this change take effect. Sudo systemctl restart Apache 2. Scan this machine again and note the output. You should see that all the TLS v1.2 protocol has also now been disabled. So congratulations, you just made a quick and easy security upgrade to your web server. End of the lab. Now let's take a look at RHEL 9 on Linux 9, hardening Apache SSL TLS and RHEL 9 on Linux 9. For this demo, you install Apache and mod SSL on Linux 9 VM. Unlike on Ubuntu, you have to install these as two separate packages. Use the same scanner VM that you used in the previous lab. A new feature on the RHEL 8.9 distros is that you can now set system-wide crypto policies for most of your web services and applications that require cryptography. We'll take a quick look at it here, and again in Chapter 7 is SSH hardening. Before doing anything, shut down your Linux VM and create a snapshot from the VirtualBox console. That's because in just a bit, you'll need to go back to a clean snapshot in order to test the crypto policies feature. On your Linux 9 VM, install Apache and mod SSL and start the service. Sudo dnf install httpd mod_ssl sudo systemctl enable --now httpd. Open port 443 on the firewall. Sudo firewall cmd permanent add service https sudo firewall cmd reload. From the scanner VM, scan the Apache VM substituting your own IP address. SSL scan 192.168.0.160. As you just saw on the Ubuntu server, nothing older than TLS 1.2 is supported. Next on the Apache VM, view the status of the system-wide crypto configuration. Sudo update crypto policies show. You should see default as the output. With default, you get TLS 1.2 as the minimum protocol version evolved with goodness of TLS 1.3. But you'll also see some TLS 1.2 algorithms that we can do without. Shut down the Apache VM, go to the VirtualBox console and restore the snapshot that you created in step 1 in order to get rid of the Apache installation. Then restart the virtual machine and set the crypto policy to future like this. Sudo update crypto policy set future. I had a great reason for having you create and restore the snapshot before setting future mode. It's just that if you install Apache before setting future mode, you'll no longer be able to start Apache. So if you want to run your Apache web server with future mode, you'll need to set future mode first, then install Apache. Reboot the Apache VM so that the future mode will take effect. Verify that future mode has taken effect by doing sudo update crypto policies show. Install the mod SSL and Apache packages and start Apache as you did in step 2. Scan the web server VM as you did in step 4. You'll see that TLS 1.2 is still enabled, but with a much smaller list of enabled algorithms. End of lab. There are two other crypto policy modes besides the two that I've shown here. The legacy mode enables some really old algorithms that we don't want to use unless it's absolutely necessary to support all the clients. But as I keep saying, anyone who's using a client that's old needs to upgrade. Important. At the time of this writing, the certificate for the EPEL repository is not compatible with future mode. You can still use EPEL, but you'll need to go back to default mode if you ever need to install or update any EPEL packages. Then you can go back to future mode. Of course, this might change by the time you read this. There's also the FIPS mode, which you might need to use if you're doing business with the US government. Even though the update crypto policy utility appears to work with FIPS mode, Red Hat recommends against doing that. Instead, they recommend setting FIPS mode as you install the operating system. We'll look at that next. Setting FIPS mode on RHEL 9 on Linux 9. FIPS stands for Federal Information Processing Standards, and it's a set of cybersecurity requirements for people and companies who want to do business with the United States government. Setting your server to run in FIPS mode involves more than just disabling some weak encryption algorithms. It also involves installing a set of modules that help harden all the aspects of the operating system. Even though the Update Crypto Policies utility has an option for setting FIPS mode, you'll never use it. To set FIPS mode on a machine on which the operating system has already been installed, you instead use the sudo FIPS mode setup enable command, but Red Hat recommends against doing that. Instead, they recommend setting FIPS mode as you install the operating system. Their concern is that setting FIPS mode after installing the operating system might leave behind encryption keys that were created with non-FIPS algorithms. Fortunately, that's easy. All you have to do is interrupt install the boot process and make a quick edit to the kernel configuration. Here's how to do it as you create a new Linux VM. Create a new Linux VM and boot up to the Linux installer. Hit the up arrow key to highlight the install Linux option. Instead of hitting the enter key to continue, hit the tab key to bring up the kernel options. Here's what you should see. Figure 6.13, the Linux installer screen. at the bottom of the screen, add fips equals 1 to the end of the kernel option line. It should now look like this. Figure 6.14, add the fips parameter. Hit the enter key and continue installation as you normally would. Once the installation is complete and the VM has rebooted, check the status of fips mode like this. Fips mode set off, check fips mode is enabled. Finally, install Mode SSL on Apache. Open the firewall, port and scan the VM with SSL scan as you did in the previous exercise. End of lab. There are a couple of caveats that you should know about when it's setting FIPS mode on any RHEL 9 type distro. One is that the current version of the FIPS standard is version 140.3. However, at the time of this writing in October 2022, RHEL 9 and its offspring will still only meet the standards for FIPS 140.2. The Red Hat documentation gives no insight into when that might change. The other caveat is that whenever a new point upgrade comes out of RHEL type operating systems, just doing a normal sudo dnf upgrade command will automatically upgrade you to a newer version. In this case, I started in this write-up with OmniLinux 9 and I later upgraded to OmniLinux 9.1. I found out by accident that upgrading a FIPS mode machine to a new point release will break the machine, causing it to no longer boot. That's because the FIPS modules were refused to load with the new 9.1 kernel. This is a prime example of why you need to always test the system updates before you deploy them on a production system. So as I can see, there's no mention of this in the official Red Hat documentation. If you're wondering why I'm not covering FIPS mode on Ubuntu, it's just that it's not possible to set FIPS mode on the free of charge version of Ubuntu. If you want to run Ubuntu in FIPS mode, you have to purchase a support contract. Now let's take a quick look at the legacy CentOS 7. Hardening Apache SSL TLS from RHEL 7 CentOS 7. Okay, I did say that we'd look at doing this on a CentOS machine, but I'll make it brief. You'll install Apache and mod SSL on CentOS 7 the same way that you did on OmniLinux 9, except that you'll use the yum command instead of the dnf command. As with OmniLinux, you need to enable and install Apache with systemctl. We won't need to enable this SSL site or the SSL module. And of course, make sure that port 443 is open on the firewall. When you do an SSL scan of a CentOS machine, you'll see a very long list of supported algorithms from TLS v1 through TLS v1.2. Even with TLS 1.2, you'll see a few really bad things like this. The DES and SHA in these lines indicate that we're supporting the use of the antiquated data encryption standard, DES, and version 1 of the secure hash algorithm, SHA. That's not good. Get rid of them by editing the etc httpd config.ssl.com file. Look for these two lines. Change them to this. Reload Apache with this command, sudo systemctl reload to httpd. Scan the machine again and you'll see a lot fewer supported algorithms. And by the way, one advantage of the new TLS 1.3 is that it completely gets rid of these legacy algorithms. Next, let's look at how users can identify themselves to a server. So they're not mutual authentication. When you access your bank's secure website, your web browser requires that the web server authenticate itself with the browser. In other words, the browser demands to see the server certificate for the website so that it can verify if it's valid. This way you have some assurance that you're logging into the bank's real genuine website instead of the counterfeit site. You don't have to authenticate yourself to the web server. You'll normally do that with a username and a password. If a web server is set up to allow it, users can instead authenticate themselves with a certificate. This way there's no password for the bad guys to either steal or crack. You already saw how this is done when you imported docstag's CA admin set the P12 certificate into your web browser. The certificate gave you the awesome power to access doctag's administrator page. Your normal end users won't have this certificate, so all they can access is just the end user web page where they can request certificates. The major web browsers, web servers, Apache, Nginx, Light HTTPD, and some other support military authentications. But it doesn't permit me to go into details of setting this up on a server, but the documentation for whichever server you will use still will cover it. Next, let's get back to the future. Introducing quantum-resistant encryption algorithms. You've likely heard of quantum computers, which have nothing to do with the old Quantum Leap show on television. This new type of computer is still in the experimental stage and likely will remain there for some time to come. Still, there's a lot of hype about what they'll be like when they finally are ready for production use. Supposedly, they'll be way more powerful than the current generation of computers, and they'll supposedly be able to easily crack even the strongest of the current encryption algorithms. Indeed, that's a rather scary prediction. Perhaps it's fitting that I'm typing this on Halloween, the scariest day of the year. Even though there's some skepticism about whether this dire prediction will come true or whether production-grade quantum computers will ever see light of day, the US federal government is taking this seriously. Here's a list of quantum-resistant algorithms that the National Institute of Standards and Technology and NIST currently recommends. Crystal's Kyber, This one is for general encryption. Cloudflare, Amazon, IBM already use it. Crystal's Delphium. This is for encrypted digital signatures. NIST recommends this one as a primary signature algorithm. Falcon. This is also a signature algorithm. NIST recommends it for whatever you need a signature that's smaller than what Crystal's Lithium can provide. Sphinx Plus. This is the third signature algorithm, which is lower and larger than the first two. It uses a different approach than the first two use, which is why NIST recommends it as a backup in case the first two get hacked. So how do we know that a particular encryption algorithm is resistant to quantum computer hacking if viable quantum computers don't yet exist? Well, I wish that I could tell you, but I can't. At any rate, you might not have to worry about too much about this just yet, but it's just worthwhile to learn. Okay, let's wrap this baby up and move on to the next chapter. Summary. As always, we've covered a lot of ground in this chapter. We began by using GPG to encrypt, sign, and share encrypted files. We then looked at various methods of encrypting drivers, partitions, directories, and shareable containers. After that, we looked at how to use OpenSSL to create keys, such as CSRs and certificates. But since we don't want to use self-signed certificates all the time and commercial certificates aren't always necessary, we looked at how to set up a private CA with DocTag. We then looked at simple ways to harden the TLS configuration on the Apache web server, and we touched on the subject of mutual authentication. Finally, we saw an introduction to quantum-resistant encryption algorithms. Along the way, we had plenty of hands-on labs. That's good, because after all, idle hands are the devil's workshop, and we certainly don't want any of that. In the next chapter, we'll look at ways to harden secure shell. Let's see you there. Questions. Which of the following is not an advantage of GPG? It uses strong, hard-to-crack algorithms. It works well for sharing secrets with people you don't know. Its public-private key schemes eliminates the need to share passwords. You can use it to encrypt files that you don't intend to share for your own personal use. You need to send an encrypted message to Frank. What must you do before you can encrypt this message with GPG so that you don't have to share a password? Nothing, just encrypt the message with your own private key, import Frank's private key into your keyring and send Frank to your private key, import Frank's public key into your keyring and send Frank to your public key, just import Frank's public key into your keyring, just import Frank's private key into your keyring. Which of the following would be the proper choice for whole disk encryption on a Linux system? BitLocker over encryptfs looks. If you use encryptfs to encrypt the user's home directories and you're not using whole disk encryption, what other action must you take in order to prevent leakage of sensitive data? None. Ensure that users use strong private keys. Encrypt the swap partition. You must use encryptfs in whole disk mode. In which of the following scenarios would you use Veracrypt? Whenever you want to implement whole disk encryption, whenever you just want to encrypt the user's home directories, whenever you prefer to use a proprietary closed source encryption system, whenever you need to create encrypted containers that you can share with Windows, macOS, and BSD users. You need to ensure that your web browser trusts certificates from the DocTag CA. How do you do that? You use PKI web server to export the CA certificate and key, and then use OpenSSL package CS12 to extract your certificate. Then import the certificate into your browser. You import the CA admin certificate into your browser. You import the CS admin certificate P12 certificate into your browser. You import the snake oil or the PEM certificate into your browser. Further reading. The explanations about TLS and OpenSSL. Problems with EV certificates. Problems with free Let's Encrypt certificates. DocTag CA. RHEL 9 or Linux 9. FIPS. Quantum resistant encryption. Answers 1B, 2C, 3D, 4C, 5D, 6A.